Thank you for the introductions. So today I will talk to you about Jacobian-Free Unrolling, which is a memory-efficient unrolling approach for unrolled networks. And this application is for 3D SPECT reconstructions. This is a collaborative work with David Saru and XTBest and Théo Caprelian, done at INSA Lyon and Creatis. So first, why do we want to do SPECT reconstruction? During the recent year, there has been radiopharmaceutical therapies who came really well adopted for cancer treatment. And we need for that accurate SPECT reconstruction to do mainly voxel-based dosimetry to calculate the absorbed dose. So for those who don't know SPECT reconstruction, SPECT imaging, it is really similar to PET imaging. It's like his little brother, we'll say. You got some projection Y subject to a forward model that is where is an image X that you want to reconstruct, knowing the projection Y. It suffers from several problems. It has poor resolution than PET imaging, mainly due to the collimation system. And so it's a bit hard. There is also a lot of portion noise in it, more than in PET. The reconstruction problematic, the reconstruction problem that we have to solve is the following. So you recognize a data fidelity term, which is the Poisson log likelihood in our case, and the regularization terms. There is several options in the literature to solve that. So the first one is the classical MLEM OSM. The second one could be the MAPIM OSL introduced by Green in the 90s, or the more fancy methods, like newer methods, such as the BSREM. There is also, since the recent years, there's also the regularization term that we have to choose. There's, of course, the Tikhonov, TV, relative difference penalty prior. And since the recent year, there is also deep learning methods. Most of them are post or pre-processing methods. And the last talk about this really clearly. They suffer from a lot of problems. Mainly, they are black box, so the lack of interpretability. They are physics agnostic, so they try to reinvent the wheel because we really know well the physics of these kind of problems. They require large training data set, which is a real problem in SPECT because we don't have access to ground truth. So for that, we are interested in unrolling methods that try to solve all of these problems in one. So the core idea of unrolled methods is to transform our optimization scheme in a neural network with one learnable component. In our case, it will be the prior, but if we are doing, for example, blind deconvolution, it could be the operator, the convolution kernel, basically. So it's really flexible. To do that, we have to solve a bi-level formulation optimization problem. So the outer problem will be the classical machine learning problems, like you try to optimize some weight subject to a loss function. And the inner problem would be the classical SPECT optimization problem. So just for the notation, if I put phi at the power of k, is the composition of phi, k time, and phi is our layer, unroll layer. So for the MAPIM OSL that we will try to unroll, this is how phi, and we try to approximate the gradient of the regularization with a CNN. So the advantage, they solve the problem that we just saw earlier. So they need small training data set, they are interpretable, and they use the physics. However, they have several drawbacks, mainly memory and computation and time. And to try to overcome this, we can look at deep equilibrium models that are another bi-level framework that try to solve the same optimization problem in the specific case where we are at the fixed point of our inner problems. It also requires large amount of memory to train it, but for different reasons. This one, it is due to the Jacobian computation and inversion in the gradient. And to overcome this, people came from, in 2022, Feng and Al came with Jacobian-free backpropagation. And to be quick, there is several links. It solves the same problem. So obviously, there is obvious link between unroll and deep equilibrium network. And David and Al in late 2025 formalize mathematically all those problems, all those connections. And to be quick, basically to solve the outer problems, we have to do a gradient descent algorithm. So that looks like this. And for the Jacobian-free backpropagations, the gradient, so G, looks like this. If you are familiar with unrolled methods, it really looks like the unrolled method gradients. And in fact, if you do one supposition that your k-1 first iteration is a good approximation of the fixed point, then it is strictly equivalent to backpropagating through the last iteration only. So in practice, there is, and we will call that Jacobian-free unrolling in the following of this presentation. So in practice, the main difference is that you are no longer limited by the number of iterations. You can do as much iteration as you want, because the memory consumption is constant, and it's approximately twice as time faster for the same number of iterations. And yeah, now you can say, okay, but this assumption that we are at the fixed point is not true in SPECT or PET. We truly never maximize the map estimation problem in those fields, and you will be right. Fortunately, there is one corollary in the original paper that says that even for poor estimate of the fixed point, we still have a Dyson direction. So that's our justification to use this kind of method. And here you have like we'll say our experiment parameters. So for the classical unrolling, we are limited to 6 iterations because we will also explode the VRAM. And for the Jacobian-free unrolling, we go from 6 to compare to 18 because we are also limited by computational time. Like, as you see, 37 minutes for one epoch is a bit longer. So it is still a supervised training task. So we still need a data set. We have no ground truth, as I said. So we basically use the work of Caprelian in 2024 to build a synthetic data set in 2 steps. The first step, we generate sources from segmented CT. And then we simulate the acquisition with simulating noise, attenuation, and PSF. It can be done analytically or with Monte Carlo simulation. So this we don't really care. So now for the results. Here you can see the loss curve for different modalities. So for the classical unrolling one, we can see that it's quite unstable. And it's mainly because the MapPM algorithm only have local convergence guarantees and that are a bit strict and are not at all verified if we put a neural network in it. And the interesting thing that we didn't expect is that if we add Jacobian-free unrolling, it seems to stabilize the training, and this effect is more pronounced, more iteration we add. So for the metrics there, we calculate several metrics such as PSNR, NRMSE, or mean NMAE. And you can see that Jacobian-free unrolling is basically, in green is the best result, in blue is the second best. You can see that Jacobian-free unrolling is basically the best one, we will say. But those metrics doesn't have any meaning in clinics, especially if we want to do quantitative analysis such as voxel-based dosimetry. So we also interested ourselves in local metrics on the arrow region of interest level, such as recovery coefficient, which is basically the ratio between the reference and the reconstructed images, and volume activity accuracy introduced by Loeb in 2024. And basically, this is the percentage of voxels that are close enough to a certain threshold, here 5%, from the sources. And you can see that on local metrics, really surprisingly, because we didn't train the network to be good on those metrics, is really significantly more performant than every other reconstruction method. Yes, sorry. And so we also conduct experimental results, test, yes. So here you can see the recovery coefficient for an experimental IEC phantoms. So this is the classical 6 spheres phantom. And we can see that Jacobian-Free Unrolling has pretty good result. It's only outperformed by the black box pre-processing method, sorry. And these black box pre-processing methods introduce a lot of artifacts, as you can see. Like there is a lot of stray artifact there and there. And so there is also some artifact with Jacobian-Free Unrolling, like there is an inverse Gibbs artifact, we call that, but we don't really know why, but they are less pronounced yet. And we also test it on real clinical data, just as qualitative example, because we don't have ground truth, so we can't calculate our metrics. And we seem to have plausible results. And so further works will be to assess this in dosimetry pipeline to see if we improve the dosimetry pipeline. So the key take-home message that I want to give you is that there is clear connection, for those who doesn't know, between DEQ and unrolled methods, and this clear connection is basically Jacobian-free backpropagation. With this, we are no longer limited by VRAM consumption. We only limited by the amount of time that we can spend to train our networks. And we can then improve also training stabilities, even for schemes that have no convergence property, basically. And also, it seems to have good quantitative performance. And for the perspective, as I said, we want to apply this to voxel-based dosimetry to further validate clinically these methods. We want to also apply this to new SPECT geometries, such as the Veriton and the Star Guide. And we want also to investigate on other algorithms, such as subset acceleration, or BSREM, and so on, and use larger networks since we have more VRAM available. Thank you. Do you have any questions?